Hi guys, welcome back to the channel. In this video we are going to discuss the SR latch using NAND gate. So let's get started. So before discussing the SR latch using the NAND gate, before that we need to understand the SR latch with the help of the NOR gate. So I hope you know this because I have already done this video. If you don't know, I am giving this video in the description box. Check it out. So this is the circuit diagram for the SR latch using the NAND means NOR gate. So with this help only we are going to build the NAND latch. Here SR means set reset. So we can simply call it as a set reset latch or SR latch. For building the NAND latch, so we are going to observe clearly the NOR latch. So in the NOR latch, if you observe for the first NOR gate, you are going to have the output expression. So if you consider the two inputs for the first NOR gate, that is S and Q, and the output is Q bar. For the next NOR gate, if you observe, we have Q bar and R, and the output is Q. So I am solving separately so that you can understand very clearly. So we are going to solve this output expression and we are going to obtain in the form of NAND format, NAND output format. So that we are going to convert this whole circuit into the NAND latch. So let's get started. The next step is that we are going to see the output expression formats. So if you also observe that we can apply there the De Morgan's law. So I hope you know the De Morgan's law. So just apply A plus B whole bar means we can split A bar into B bar, like that we can split. So if you observe there is S plus Q whole bar, so we can split like that as S bar dot Q bar. So that equals to Q bar, already we have that. So for the second NOR gate we can also split according to the De Morgan's law. So after splitting that, it is Q dot R bar is equals to Q. So this is just simply the NOT means the NAND gate. So simply represent with the help of the NAND gate, the two NAND gates. So our aim is to implement the latch with the help of the NAND gates. So we already got with the help of AND gates. Just complement will get the NAND gate. For that purpose, if you observe, we are going to have the NOT gate also in this. So the final output for the first one is Q. At first we are getting Q bar, but after adding NOT gate, I have took directly the Q. If you observe in the second NOR gate, that is Q bar exactly. So you can simply see that we can also cascade both of them, because these are the two things that I have separately done for your simple understanding, but actually both are cascaded. So let's do the cascading. So I hope you can understand or relate now. So these are both cascaded, or if you observe the inputs and outputs also, you can relate them, or you can understand both are cascaded. So in the first NAND gate, if you observe S bar Q, so if you observe that clearly, we have one input Q bar and one output Q. So if you observe the next one, that is two inputs as Q R bar and output is Q bar. So you can simply cascade this the second output with the first input and the first output with the second input. So the inputs would be S bar and R bar. So I hope you can relate with this NOR latch. But very important thing is here is the inputs are not a true form, that is complemented form, that is S bar and R bar. For your understanding purpose, I have done separately, but both are same. If you observe both the NOR latch and the NAND latch, if you observe somewhat similarities. But here if you observe, the inputs are S bar and R bar here, because in that also if you see, the inputs are S bar and R bar. So these are known as active low inputs, and outputs are as it is, that is Q and Q bar. Finally we have obtained the NAND latch. So after obtaining, we should know first the NAND truth table, so that we can understand or we can implement the truth table of the SR latch. So if you observe the NAND truth table, so basically if any of the input is 0, the whole output becomes 1. So this is very important point that you should know. If any input is 0, the whole output becomes 1. So let's see the truth table of the NAND latch also. So I hope you know the NAND gate truth table, but this is the SR latch truth table. So if you observe, if you pass SR as 0 0, output would be forbidden. So 0 1, here just exactly opposite of the NOR gate, means NOR truth table. 0 1 means it will be set, 1 0 means it will be reset, 1 1 means it will hold the previous state, PS means previous state, NS means next state. So we will also verify the truth table with the help of put each and every value in the circuit diagram, and we are going to verify the outputs. Before that, you might get a doubt. In any of the textbooks and majority of the places, you might see the inputs are just S and R, not S bar and R bar, because those are not normal inputs. Those are called active low inputs. Means those are will be active when inputs are low. That is the meaning that we can say. So active low inputs means function is activated when the input signal is low, 0 instead of 1. So if you observe SR are known as active high inputs. It will work when S and R are active. So if S bar and R bar are known as active low inputs. So these can be simply represented as SRR also, but indicating that as active low inputs. For the simplicity purpose, they will simply represent SR as inputs and they will mention that as active low inputs. So that we have to understand active low means those are S bar and R bar only. So you can also observe that I have mentioned that inputs as active low inputs. Means instead of representing S bar and R bar as inputs, so simply I represented as SR inputs. So you can also, now we are going to verify the SR NAND latch truth table. So first we are going to put S as 0 and R as 1 in the circuit diagram and we are going to verify the outputs. So if you first see as I am passing, so we already know the NAND gate truth table. If any one of the input is 0, the whole output becomes 1. So we have already seen this NAND gate truth table and we also know that before because it's a basic universal gate. So the S is equals to 0 here. One of the input is 0. So we don't care the remaining inputs. So the whole output Q would be definitely 1. So when one of the input is 0, just start there and come back, means take feedback from the output and you are going to have the next output also. So if you consider when one input is 0 here, that is yes here, so simply we are going to have Q is equals to 1 because that is one input is 0. We don't care the remaining input. So you have obtained the Q. So take feedback Q to the next NAND gate. So that is means 1.1 whole bar, that becomes our Q bar as 0. So in this case you can also observe in the truth table that as Q as 1. So when one of the input that is 0 1, S is 0, R is 1, the whole output Q is equals to 1 in the next state. The next thing we are going to see is we are going to pass the 1 and 0 as S and R and we are going to verify the Q and 0. So here also when one of the input is 0, then whole output would be 1. Already we have know the NAND gate formulas. So if you observe, we are going to start with R because here R is 0 first. That I have highlighted in the blue color also. So we don't care or we cannot see we won't see the second input also. Simply we are going to have obtain the Q bar as 1. So if Q bar is 1, definitely Q would be 0. No need to check. So if you want to check also, simply we can check. Like we can have a feedback to the first NAND gate. If you see clearly, the feedback is 1. So already S is 1. So the feedback is also 1. So 1.1 whole bar is Q is equals to 0. So we can see that S is 1, set is 1, reset is 0 means the whole output Q is equals to 0. You can also see in the truth table also. And the next one is we are going to check when S is equals to 1, reset is equals to 1. When both set and reset would be 1, then what we are going to obtain as output. So if you consider for these situations, we are going to have the Q and Q bar as the presetted value by us. So for the first condition, we are going to take Q is equals to 0 and Q bar is equals to 1. So this is the just assumption. Vice versa is also possible. So first let's see with this, after we are going to see vice versa also. So vice versa means Q bar is equals to 0, Q is equals to 1. Basically if you observe in the truth table, we are going to get the output as hold. Hold means the previous state will reflect as the next state also. So here the present state is Q is equals to 0 and Q bar is equals to 1. So after performing our operations also, we are going to get the next state also is the same thing. So let's check we are getting the same thing or not. If you observe here clearly, we have took the present state as 0 and 1, means 0 as Q bar as 1. So just take the feedbacks over there. So if you see the first NAND gate, that would be with the help of the feedback also, you can see 1 into 1 whole bar gives our 0 output. So Q is equals to 0. If you observe the second NAND gate, that 1 into 0 whole bar, that Q bar is equals to 1. So if you also observe the present state and the green highlighted one, that is also next state would be the same. That is Q is equals to 0 and Q bar is equals to 1. So that is known as hold situation. Whenever present state and next state are equal, that is known as hold the present state. I already said. So vice versa is also possible. So now let's see the vice versa. That Q is equals to 1 and Q bar is equals to 0. So that is the present state. If you observe, just I took that also in there directly. So if you observe, just take the feedbacks and just do the same thing. So if you observe the second NAND gate, that is 1 into 1 whole bar, that is Q bar is equals to 0. So of course definitely when Q bar is equals to 0, Q would be 1. Also you can also check with the just 1 into 0 whole bar, that is also the 1 output. So what does this mean? Here also the next state would be 1 and 0, the same as it is the previous outputs, and the present outputs also same. So this is known as hold condition. When both of the inputs are for 1 1. In the truth table also you can verify. And finally we are going to verify when S and R are 0 0, we are going to check forbidden state. So let's understand what is meant by forbidden state. So if you pass directly S and R are 0 set and reset at a time 0 0, so you can take the feedbacks directly. So you can see that when Q and Q bar are 1, both are 1. So definitely that would not be possible because both are in complement forms. So definitely Q is not equals to Q bar. Definitely 1, if 1 is 0, and that should be definitely 1. So that is the rule. So this is known as forbidden state. When both of the conditions are not satisfied or both of the conditions are equal, that is known as forbidden state. Means it is not possible, we are not going to take as inputs that condition. Just for studying purpose we are representing that. As in the NAND latch, we have two inputs and two outputs. S R as inputs, Q bar as outputs. So we can simply have the like a box type. That is the simply block diagram representation. So instead of representing the whole diagram, circuit diagram, this is a simple way of representing the NAND latch. So all the latches will be same as this kind. And one more important thing, up to now what we have saw the NAND latch is known as the transparent SR latch or transparent NAND latch, because it is very transparent, means it will respond to input levels very immediately. So this is known as basically asynchronous sequential memory element. Basically latches and flip-flops are memory elements that we already know, but this latch is immediately respond to input level that we doesn't want. Because if it responds immediately to the input levels, then what is our requirement? That cannot be fulfilled. For that purpose only we have another kind of latch that is known as gated SR latch. So this is the basic block diagram of gated SR latch. All this latch is same, two inputs, two outputs, but additionally we have one thing called enable. So this is known as a synchronous sequential memory element, just adding the enable input. So this responds to the inputs only discrete time intervals. So this is the condition that we are required. So we can also convert the normal latch, the transparent latch, to the gated SR latch with the help of this kind of block circuit diagram. So simply add two NAND gates to the normal SR latch with the help of the enable line by connecting two inputs. So already we have saw what is inside the box of SR latch, the transparent latch. So simply replace the SR latch box with transparent latch with the already something. So that becomes our final output thing of gated SR latch. So this is the circuit diagram that I am talking about. First, if you see the S and R are the real inputs, and S dash and R dash are the inputs to the transparent latch, and Q bar is our final outputs. So if you observe that the first NAND gate, that is S dot 1 whole bar is equals to, according to the De Morgan's law, S bar plus 1 bar is equals to S bar. In the same format, if you observe the R also, that is they are converting to the complement forms. So if you send S, we are getting S bar. If you send R, we are getting R bar when enable is equals to 1. You can also observe in the truth table also. So this is the truth table for the gated SR latch with the help of the NAND gates. And the last state is forbidden state. This truth table is exactly opposite of the transparent latch truth table, because we are passing the real inputs and we are getting complement inputs, and finally we are passing the complements inputs to the latch. So let's observe that. So if you observe, we are passing S and R, that is known as active high inputs, because that is normal inputs only. So if you observe inside the box, that is known as transparent latch, S bar and R bar. So you also observe now only the conversion. So actually S dot 1 whole bar. So that is basically with the help of the NAND gate. E is always 1. When E is 1 only, whole latch will be working. So actually we are sending normal inputs, but we are getting complement inputs. So that is known as transparent latch with the active low inputs. Then now you might get a question that why this truth table is exactly opposite of the transparent latch for the gated SR latch. So if you observe clearly, in this first case we are passing 0 0. Always enable is 1. Enable is 0 means the latch will not work. So when the case has R S is equals to 0 and R is equals to 0, you can see that is in this case we are getting hold. But in the transparent latch, that is another thing. So why, I will explain now. Because when you are sending S and R as real inputs as 0 0, so just complement both of them. That in the transparent latch you are getting the sending inputs as 1 1. So already we saw when we are sending 1 1 in the transparent latch, we are getting output as what? That is the hold condition. So the same thing we are getting output in this case also. So if you have doubt, check over this. So this is the transparent latch we have already done. When we are sending transparent latch as 1 1, we are getting output Q is equals to 1. So for the understanding of gated SR latch, you need to remember or recall the transparent SR latch outputs. For the understanding purpose, we are going to send the next input, that is S is equals to 0, R is equals to 1. So after sending, just invert both of them. Then it becomes S is equals to 1, means the S dash, means the inside for the transparent latch inputs I am saying. So first upper one is 1 and for the down transparent latch is 0. So the output would be 0 according to the transparent latch inputs. If you observe in the truth table also, we are having the output as 0 for the gated SR latch. So finally, if you pass as SR as 1 1, so you are going to reverse both of them. That you, after reversing, you are going to have 0 0 inputs to the transparent latch. So we have already seen if both inputs are 0, that conditions becomes the forbidden state for the transparent latch. The whole output becomes the forbidden. So that is the latch situation. So when both of the output becomes 1 1, that is not possible. That is forbidden state. Finally, I hope you understood the transparent latch and the gated SR latch with the help of the NAND implementations. Thanks for watching up to now.